Alright, let's get started. Question 1. So a cyclist travels at a constant speed along a horizontal ground. When they say that it's a constant speed, it means that acceleration is 0, hence resultant force is 0. F net is 0. Frictional forces oppose the motion of the cyclist. Alright, so your resistive force would be the frictional forces. Could be due to air resistance, could be due to any other thing. Use Newton's first law of motion to explain why the cyclist travels at a constant speed. This question has 2 marks. So you require 2 points. The first point, you will give the definition of Newton's first law of motion. Newton's first law of motion states that a body will remain in its state of rest or uniform speed in a straight line unless a resultant force acts on it to change its state. So that's your first mark. Define Newton's first law. Next, you would explain that the resultant force on the cyclist is 0. Hence, it will remain at a constant speed. So first step, define Newton's first law. Second step, since the resultant force acting on the cyclist is 0, the cyclist travels at a constant speed. There we go. Pretty simple. Just Newton's first law. And then we'll move on to the next question. Okay, big formula, looks kind of complicated, but let's break it down. The drag force F acting on the cyclist at a speed v is given by F equals to 1 over 2 c to the d density times big A times v squared. What could all that mean? So okay, it's not important. Oh, this is here. Drag coefficient, density in frontal area. Okay. So what does the question want? Determine the speed of the cyclist with its actual uncertainty. Okay. So the question wants to find the speed, and speed here would be v. So we need to solve for v. Okay, let's do that right now. Starting from the initial formula, F equals to 1 over 2 drag coefficient, density of air, area, v squared. So we'll move everything here to the other side. V squared would equal to 2f over c density A. V equals to 2f c density A to the power of 1 over 2. Alright. And the question wants the speed and its uncertainty. So it will be in this format. It will be v and the uncertainty of v. So we can solve for v straight away by plugging in all the numbers. Here are the numbers. So if you work out the calculation, you will get 11.411 meters per second. Leave it to 5 SF. Alright. Next, the tougher part that, students tend to make mistakes on is finding the uncertainty. So how do you find the uncertainty? We have this expression here, and so we'll be using this expression. So we'll be using this to find the uncertainty. We'll start off by writing this. Delta V over V is equal to delta F over F plus delta C over C plus delta A over A. Now, there's some things missing, as you might have guessed. Oops. So, where did this 2 go in the expression? Since 2 is a coefficient, is a constant, when finding the uncertainty associated with velocity, we can just ignore it, it just disappears. Then what about this 1 over 2? We will actually bring it down right here. Okay, so this is the tough part. It's basically finding out the arrangement of the formula, and yeah. So the next step is to plug in all the numbers and to solve for delta V. Right, let's do that. So delta V over V equals to 1 over 2. You can just straight away throw in all the numbers. So it's 2 over 22 plus 0.01 over 0.88 plus 0.1 over 1.2 plus 0.02 over 0.32. Okay, and what about this V? This V here, we actually found it in the previous part, so you can plug in that also, and you can arrive at delta V to be 1.4149. Okay, so that's 3 marks already. You got your 3 marks. The last mark is the answer mark. So how do you answer the last question? Very simple. For uncertainty, you will round it off to 1 SF, which is just 1. 1 SF. So delta V will just be 1. What about the V itself? So the number of decimal places that delta V has is 0. So for V, we will follow that and have 0 decimal places for V. So it will be 11. Everything after the decimal point is not considered. So that's it. So your 4 marks. Okay, next. Derive from the definition of work done an expression for power output of the cyclist in terms of velocity V. Definition of work done is the force, the product of the force and the displacement in the direction of the force. So W equals to F times S. They want an expression for power output. So what's the formula for power? Formula for power is energy over time. And energy is actually in the form of work done as well. So we work done over time. Okay. So if we were to compare this one and this one, what's the difference? The difference is that the one on the left hand side is missing a missing a time on the denominator. So we can just do that. Divide both sides by t. And look at that. We get power on the left hand side, and you get force times displacement over time. If we were to rearrange it, we'll get force times displacement over time. And as you know, displacement over time is actually velocity. So there we go. That's the expression. Calculate the power output of the cyclist at the speed calculated in B. So the speed calculated in B is 11.411. P equals to FV. What about the force? The force is 22. So we will take 22 times 11.411, which will give us 251, round off to 2SF. Why 2SF? Because you want to follow the least SF. 22 has 2SF, so we'll write 2SF. 250. Okay, good. Alright, next question. Define gravitational potential at a point. Gravitational potential is the work done per unit mass in bringing a test mass from point of infinity to the point in the gravitational field without a change in velocity. Alright. So some students might find it to be difficult to memorize the difference between gravitational potential energy and gravitational potential definition. So what's the difference? We'll start off with gravitational potential energy. Gravitational potential energy is sort of self-explanatory. Energy is like work done, they're equivalent, the units are the same. So gravitational potential energy is the work done in bringing a test mass from point of infinity to a point in the gravitational field. Now let's examine the difference between gravitational potential energy and gravitational potential. Potential is negative gm over r. So what's the difference? The difference is the small test mass, right? So if we were to imagine it like this, it would be like adding an additional m on the denominator so that it cancels out. So that's where the per unit mass comes from. The per unit mass is because the mass is in the denominator. Yeah. So that's how you can remember. Next question. The Earth of radius 6,400 kilometers is a mass. The global positioning satellite of mass is in an orbit of radius this about the center of the Earth. The satellite is launched from the Earth's surface. Change in GPE. So whenever you see the word change, first thing you should do is to think about final minus initial. Change is final minus initial. Change in what's that? Change in potential energy is potential energy final minus potential energy initial. And the formula for gravitational potential energy is negative gmm over r. So negative gmm over r final minus by negative gmm over r initial. So we can actually factorize out negative gmm, or rather, to make things simpler, we can flip it. Gmm over r initial minus gmm over r final. That looks simpler. Factorize out gmm to get 1 over r initial minus 1 over r final. Alright. Now g is the gravitational constant, sub that in. The mass, the big M is the mass of Earth, which is 6.0 times 10 to the power of 24. And the small m is the mass of the satellite, which is 1,600. We'll multiply this whole thing by 1 over its initial radius. Its initial radius would be 6,400 kilometers. So you take 6,400 times 10 to the power of 3, because it's in kilometers, minus by 1 over the final radius, which is 2.7 times 10 to the power of 7. So plug the numbers into the calculator, you will arrive at 7.63 times 10 to the power of 10 joules. And follow least SF, 2.7, 6.0, 2SF. So you'll get 7.6 times 10 to the power of 10 joules. Alright. Next. A satellite of mass m orbits a planet of mass m. Big M. The mass of the planet may be assumed to be a point mass at its center, so that Ke is given by this thing. Okay, so the satellite is orbiting a planet. So you should link this question to circular motion. because the gravitational force exerted by the planet on the satellite provides for the centripetal force required for the satellite to go in circular motion. So, you start off by saying the gravitational force provides for centripetal force. Please do write out gravitational as a whole as well as centripetal. Yep. So the formula for gravitational force is Gmm over r squared. Small r, because the question is using small r. And circular motion, the formula for circular motion is mv squared over r. Alright. So the question wants us to find Ke. Ke is half mv squared. So if we were to examine the formula that we have, this part here, it looks similar to what we want. It's just missing one small component. So we should rearrange the formula around this mv square. So we will multiply both sides by 1 over 2. So we'll get half Gmm over r squared equals to half mv squared. Oops, small arrow. Alright, I moved the r out of the equations so that it's easier to see. So the next step that we need to do is to just move this r over to the other side. Then we'll simply get half mv squared equals to g m over 2r. Yep, that's it. Shown. Next, use the information in B and the expression in C part 1 to calculate Ke of the global positioning satellite. So what do we need? We need mass of the planet, mass of the satellite, as well as the radius of orbit. The mass of the planet is using the information in B. So the mass is 6.0 times 10 to the power of 24 multiplied by the satellite's mass, which is 1,600 kilograms, Gmm, all over 2r, where r is 2.7 times 10 to the power of 7 meters. If you were to work this out, you will arrive at a value of 1.186. Times 10 to the power of 10 joules. Once again, round off to 2SF. Nice. Okay, so a student wants to calculate the change in kinetic energy of a satellite launched from the Earth to its orbit. The student calculates the initial and final kinetic energies using the expression in C part 1. Suggest and explain whether the student's method is correct. So it would be incorrect. Why is it incorrect? It is because the formula used to calculate the kinetic energy of the satellite in orbit cannot be used when the satellite is on Earth. The formula came from the assumption that gravitational force provides for centripetal force. And since the satellite on Earth is not undergoing circular motion due to gravitational force, so this formula cannot apply. Incorrect. So the satellite is not undergoing circular orbit. The formula can only be used when a body is undergoing circular orbit due to gravitational force. Alright, for question 3, two parallel plates are in a vacuum. One plate is positively charged and the other plate is Earth. A rectangular conductor of width x is placed midway between the plates so that its faces are a distance x from each plate as shown in figure 3.1. You can see the diagram here. On the left side you have the positively charged plate, on the right side you have the plate that is Earth, meaning it will be negatively charged, or rather no charge. So, and then after that the conductor is placed right in the middle. Okay. The variation with distance from P to Q of the electrical potential along line PQ is shown in the figure 3.2. There's a constant gradient that is going downwards. Alright. On figure 3.2, draw a line to show the variation with distance from R to S of the electrical potential along line RS. So if we're looking at RS here, you can see that the electrical potential, the E field strength goes this way, so it passes through the conductor. And inside the conductor, let's draw another diagram on the side. So the E field passes this way, from positive to negative. Inside the conductor, there are electrons. So since opposite charges attract, the electrons will gather on the left hand side of the conductor. And so the right side will be more positive. So there's an E field going to the left. There is also an E field going to the right, as shown here. So, since electrical fields are a vector, they essentially cancel out. So the E field strength inside the conductor is 0. And as we know, E field strength is directly proportional to the negative potential gradient. So if E is 0, it will imply that the electrical potential is constant. And where is it constant at? It's constant at this region here. This region. Or rather, just this region here. Alright. So essentially, we will have a straight line from x to 2x. But the problem is, where is this straight line supposed to be? It's very simple. The E field strength between the two conductors are uniform. Meaning if this part had to be a straight line, it would imply that it will be right in the middle. how do you find the middle? Count by the units. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 here. 1, 2, 3, 4, 5 here. 5 here. 5 here. 5 here. 5 here. Alright, so there's 1, 2, 3, 4, 5, 6. So half of 6 is 3. That's how we arrive at this one here. And then all we have to do is just join up the lines like this and like this. There we go. As simple as that. Okay, for part B, the variation with distance from P to Q of the electric field along line PQ is shown in figure 3.3. It's not very clear, so I will draw it. I'll highlight it in blue. Okay, now they want us to draw the line to show the variation with distance from R to S of the electric field strength along line RS. So as previously discussed, in the conductor, the E field strength is actually 0. So we can start off by drawing 0 right here from X to 2X. Okay. Next, we need to figure out what is the value for the electric field strength from R to S. Right. Okay. So if you look at this previous graph, you can see that if you just focus on this portion here, from here to here to here. Yeah, let's just focus on this portion. If you were to look at the black line and try to find the gradient of this line, it would be, sorry, let's just change this to V. The gradient of the black line would be 1/3 of V over X. 1/3 of V over X. Alright. And the gradient for the red line would be 1/2 of V over X. So we can tell that the gradient for the red line is steeper. So we can find the difference in electrical field strength by comparing how much larger the red line's gradient is compared to the black line. So we will do that by taking 1/2 V over X divided by 1/3 V over X. So it will just be 3/2 or 1.5. Meaning to say that the gradient for the red line is 1.5 times that of the black line. So since electrical field strength is equals to the phi over dr, since phi is since the phi over dr for the red line is 1.5 times that of the black line, it means to say that electrical field strength of the red line is equals to 1.5 times of the E field strength of black line. Yep. So 1.5 times of 4 would be 6. So it would just be like this. And like this. Oh, that's it. Alright, moving on to the next question. Question 4a. Explain what is meant by the term diffraction. So, diffraction refers to the spreading of waves as it passes through an aperture or obstacle. There's one more point to it. It is observable when the order of wavelength has the same magnitude as the aperture or obstacle. Alright. State two conditions necessary for two source interference fringes to be observed. The first one is the waves need to be coherent. They need to be coherent so that they have a constant phase difference. Next one. The waves should have same amplitude for good contrast between areas where constructive or destructive interference occur. Alright. Next. A laser is used to produce two source interference fringes on a screen. So two source interference. It would imply that it is a double slit, yeah. The incident laser light is normal to the plane of a double slit, okay? The plane of the double slit is parallel to the screen. The variation of the fringe width x with distance d between the double slit and the screen is shown in this figure. The separation A of the slits is 0.12 millimeters. Calculate the wavelength of the laser light. So, in a double slit experiment, the first formula that you would think of would be this. X equals lambda d over A. And is x given? Yes. Is d given? Yes. Is a given? Yes. And what are they looking for? Looking for lambda. So everything's given to you. We just have to rearrange the formula to figure out what we want. So lambda would be x over d times a. And what's x over d? X over d is y over x. It's actually the gradient of this graph. So this position here, the x coordinate is 2.0, y coordinate is 8.8 times 10 to the power of minus 3. Then for here, x coordinate 1.0, y coordinate 4.4 times 10 to the power of minus 3. Okay, just plug it in. .8 minus 4.4 times 10 to the power of minus 3 or over 2.0 minus 1.0 multiplied by A, where A is 0.12 millimeters. 0.12 times 10 to the power of minus 3. We will get 5 0.28 times 10 to the power of minus 7 meters. Run off to 2SF. And there we go. Okay. Next, a filter is used so that the amplitude of light from one slit is halved. Calculate the ratio of maximum intensity of the central bright fringe and the maximum intensity of the adjacent dark fringe. So, since we are given the amplitude, we will work with the amplitude first. So for maximum amplitude, it will be the amplitude from one light source plus the amplitude from the other, which will give us 1.58. Then the amplitude minimum will be this. So one is 1.5 amplitude, the other one is 0.5 amplitude. As we know, intensity is directly proportional to amplitude squared. So in order to find I max over I minimum, it would just be amplitude max over amplitude minimum holding squared 1.5a over 0.5a squared, which would just give us 9.0. Done. Nice. Alright, for the next question. A silver wire of length 0.42 meters has a diameter of 0.38 millimeters. The number density of free electrons in silver is given by that number. The drift velocity of electrons in the wire is 7.2 times 10 to the power minus 5 meter per second. Okay, so we have length L, we have diameter D, we have the number density, which is N, we have drift velocity. Alright, so this looks oddly familiar. I equals to N A V D Q. Okay, so we can basically find the current within this wire. The number density N is given by 5.9 times 10 to the power of 28. The cross-sectional area, cross-sectional area is not given, but we can derive it from this. Alright, so area, as we know, is pi r squared, and r is actually half of d. So you'll get 1/4 pi d squared. Nice. So sub it in. 1/4 pi multiplied by d, 0.38 times 10 to the power of minus 3 whole thing squared, multiplied by the drift velocity, which is 7.2 times 10 to the power of minus 5, multiplied by the elementary charge of the electron, which is 1.60 times 10 to the power of minus 19. We will arrive at 0.007708 amperes. Right, so we found our current, but the question wants us to find charge. So we use this formula, I equals Q over T. Q equals to IT, which is 0.07708 multiplied by time. The time is given to be 30 minutes. So we'll multiply it by 30 times 60, because in every minute there's 60 seconds. Right? We will get to a value of 139 coulombs. As always, 2SF. Right, next question. An AC power supply is connected to 3 resistors as shown in the figure. Okay, the variation with time of the voltage V of the power supply is given by the expression shown, this expression. For the power supply, determine the frequency F. Okay, so if you were to look at your data formulae, you can see this one being given. X equals to X naught sine omega t. This is the formula for alternating current slash voltage, right? So if you just compare these two, you can see that omega is equal to 120 pi. What else does omega equal to? It equals to 2 pi f, right? 2 pi f equals 120 pi, right? Then the f comes out. F comes out to be 60 hertz. Simple. Alright, next. Next, they want us to find the VRMS. So, just memorize. VRMS equals to V naught over root 2. And what is V naught? V naught is the second value here. It's the one with the subscript O or subscript 0. So just throw in the number 9.0 over root 2 and you will get 6.36 volts. Round it off to 2 SF. Nice. Alright, now they want us to calculate the peak current. So, peak current, I equals V over R. So peak current equals to peak voltage divided by total resistance. Do we have V naught? Yes, we do have V naught, which is 9.0. Do we have resistance total? No, we don't. But the value for the resistors were given to us, so we can figure that out. We will first consider these two, right? So how to find the resistance, the effective resistance? 1 over R effective equals to 1 over 6.0 plus 1 over 12. So the effective resistance is 1 over 6.0 plus 1 over 12 all to the power of minus 1, which will come out to be 16 ohms. Wrong. It will come out to be 4.0 ohms. And the total resistance, you just have to take 12 plus this, which will get 16 ohms. Okay. So as we know, V naught was 9.0, R total was 16, and that's it. If you work out the math, you will get 0.563 amperes. You know the drill. Next, they want us to calculate the mean power dissipated in the resistor of resistance 6.0 ohms. Now, alright. So mean power. Let's write down the formula for mean power. So basically you have to choose between one of these formulas in order to find your mean power. For this question, using VRMS would be easier, and I'll show you why. So in order to find the potential difference across the 6.0 ohm resistor, we can actually consider this whole thing to be one main resistor, right? The effective resistance for this big resistor is 4.0 ohms, while the other one is 12. So we can just do some quick calculation, the ratio. The potential difference across the 4.0 ohm effective resistance is, well, 4.0 over 16 multiplied by 6.36 here. Which we will get 1.6 59 volts. Okay, so basically what that calculation tells us is that the potential difference between here and here is 1.59 volts. From here to here, also 1.59 volts. Why? Because voltage in parallel circuit is constant. Okay, so since we got our VRMS across the 6.0 ohm resistor, we can just sub it in and find our answer. So mean power would be 1.59 squared all over R, where R is for 6.0. And we'll get 0.421 watts to SF. Done. Okay, question 6, define magnetic flux density. So we start off with the formula F equals to BIL, rearrange it to get B equals to F over IL. So if you just look at the formula, magnetic flux density is equal to the force per unit length acting on a current carrying conductor that is placed at a right angle to the magnetic field. Why must be right angle? Because there's actually a hidden sine theta here. But since sine of 90 degrees is equal to 1, that's why it disappears. Yeah, so stating that it is at a right angle to the B field is actually important. Next. A long solenoid of diameter 4.0 cm has 520 turns of insulated copper wire. The diameter of the wire is 0.46 millimeters. The wire is wrapped in a single layer with no gaps between each of the turns. The copper wire has resistivity 1.7 times 10 to the power minus 8 ohm meters. Calculate resistance R. So you see resistance R, you see resistivity, the formula straight away pops up. So what you should be using is R equals to rho L over A. Do we have rho? Yes. Do we have L? No, we don't have L. So let's find what's L. L is the total length of the wire. And you can imagine it like this. Let's draw a diagram. This is the solenoid. And this is the wood. This solenoid has a diameter of 4 centimeters. And the coil is wrapped around and around. Of course, much more like tight to each other. But for illustration purposes, I will spread them out so it's easier to see. Okay, and it wraps around 520 times. So, in order to find the length of wire used for one round, we essentially have to find the circumference of one circle. So the circumference of one circle would be 2 pi r. 2 pi r, which is, never mind. So okay, so that's one circle. And since there's 520 circles, we just have to multiply this number by 520. Alright. And as we know, 2 pi is actually the diameter. So it's just this. And the diameter is given by 4.0 cm. Do the math. 65.345 meters. So that's our L. Next is the cross-sectional area. Well, cross-sectional area is simply pi r squared. However, r is given in the form of diameter, so I have to change r to d. So it will just be 1/4 pi d squared, which is equal to, which is equal to 1/4 pi multiplied by 4.0 times 10 to the power of minus 2 squared. Then you will get 1. It appears I've made an error. The diameter that I'm supposed to use is of the wire itself, not the solenoid. So it will be 0.46 times 10 to the power of minus 3 squared. Okay, that looks better. Which then you will get 1.662 times 10 to the power of minus 7 meters squared. Great. So we have all the components. Simply have to throw everything in. Rho is given by 1.7 times 10 to the power of minus 8. L is given by 65.345. And A is 1.662 times 10 to the power of minus 7. R will be 6.68 ohms. 2SF. Great. Next, the solenoid in B is connected to a 24-volt supply. Use information from Papi to calculate the magnetic flux density along the axis of the solenoid. So, if you want to find the magnetic flux density of the solenoid, you can use the formula given in the data booklet. B equals to mu naught times N times I. So we run to our first problem. What exactly is I? Well, it's quite simple. I equals to V over R. V is 24, R is 6.68, which will give us 3.593 amperes. Alright, now the next part is finding N. N is the number of turns per unit length. Number of turns per unit length. So N is equal to 1 divided by So what do they mean by number of turns per unit length? It just means given a 1 meter length solenoid and using a wire of a certain diameter, how many times can I wrap this wire along the solenoid before it reaches 1 meter? So we simply have to take 1 meter divided by the diameter of the wire. And the diameter of the wire is 0.46 millimeters, which gives us 2174. Just plug everything in. The mu naught permeability of free space is given. 4 pi times 10 to the power of minus 7 multiplied by number of turns per unit length multiplied by the current. We will arrive at 9.82 times 10 to the power of minus 3 Tesla. Remember, the unit for magnetic field strength is Tesla. Good. A current carrying wire is placed inside along the axis of the solenoid in B. The solenoid remains connected to the 24-volt supply. State and explain the magnitude of the force, if any, experienced by the wire. Okay, so you'll draw the same solenoid here, and it's wrapping around this way. It's wrapping around this way. Alright, if you were to use your right hand grip rule, the wire is turning, well, it's turning towards you. It's coming over from the top, turning towards you, so your thumb should be pointing to the right side. And since the current is going in this direction, in this circular direction towards us, your thumb points to the right, which means to say that the B field the B field is pointing to the right. The B field is pointing to the right. Alright, now they insert this new wire within the solenoid, and it's carrying a current in the same direction. Now, if you were to use your Fleming's left-hand rule, force field current, force field, the B field is pointed using your index finger. The current is in the same direction as the B field, which means to say that it is not perpendicular to the B field. And since the B field and the current, the directions are parallel to each other, there will be no force produced. The wire does not experience any force. Right? So simply say that the wire does not experience any force. It is because the B field and current in the wire are parallel to each other, using the formula F equals to BIL sine theta. Since theta equals to 0, F equals 0. That's it. Alright, question 7. Explain what is meant by a photon. So, a photon is a quantum of electromagnetic radiation, and it contains an energy which is equivalent to HF, where H is Planck's constant and F is the frequency of radiation. Alright, next. A beam of white light passes through a cloud of gas. The spectrum of the transmitted light contains a number of dark lines. Explain why these dark lines occur. So, this would obviously be an absorption spectrum, since only certain wavelengths of light were absorbed. Right. So, explain why these dark lines occur. When the beam of white light is incident on the gas, some of the photons in the white light have an energy HF, which is equivalent to the difference in energy level of the gas atoms. So this results in an electron in the gas to be excited. The electron in gas is excited to a higher energy level. However, the electron is unstable. Hence, it will de-excite to a lower energy level. In the meantime, when it de-excites from a higher energy level to a lower energy level, a wavelength of light that is equivalent to the difference in energy level will be emitted. However, this wavelength of light is emitted in all directions, which means that lesser photons are in the same direction as the beam of white light. Alright. So, compared to the unabsorbed photons from the light, rather when the light is diffracted, diffracted into a spectrum. The absorbed wavelengths of light will appear as black lines. Alright, that was a lot. So let's try to recap what's happening. I'll draw it here. So a beam of light contains, a spectrum of different energy wavelengths, energy photons, and they come into contact with the atoms within the gas. So this is what the energy levels within the gas look like, right? So when the photons come into collision with the electrons will gain energy, right? And it will be excited. By how much will it be excited? It will be excited to an energy level where the difference in energy level is equivalent to the energy of an incident photon, right? So it could go here, it could go here, it could go here, it could go anywhere, as long as the energy of the incident photon exactly correlates or exactly is the same as the difference in the energy level between two energy levels inside the atom, right? So once they get excited, the electrons are unstable. So what happens when they are unstable? When they're unstable, you want to fall, right? You're going to fall down. So let's say we have some photons at E3, energy level 3. They could fall like this, they could fall like this, right? And each of this difference in the energy level, once again, it corresponds to an energy of the photon. So you will release a wavelength of radiation that corresponds to the difference in energy level, right? And it will be re-emitted in all directions. So you can imagine, let's go back to the cloud drawing here. You can imagine the photons coming into the gas, some stuff happens, and after that it gets re-emitted. It gets re-emitted in all directions. Then the beam of light just continues on. After that, it reaches the spectrum, right? So the amount of light that is being re-emitted after the electron falls from a higher energy level to a lower energy level is actually lesser. It's lesser when compared to the amount of photons that are traveling in the beams that are unabsorbed, right? So since the number of photons traveling in the same direction as the beam is lesser after they have been re-emitted in all directions, it will hence appear as dark lines after the light is being passed through a prism, to observe the spectrum. Yeah. Okay. Next. Some electron energy levels in a hydrogen atom are illustrated as this energy level given an expression. Okay. Calculate the energy in EV of energy level 2. So we just sub in the number. All over 2 squared. This will give us 3 negative 3.4. negative 3.4. Okay. Determine the wavelength of light absorbed when an electron in energy level 2 is excited to energy level 3. Okay. From 2 to 3. So the electron is initially here, then it's excited to energy level 3. So energy level 3 has higher energy level. Yeah. Okay. Let's calculate the energy level at 3 is this. You get negative 1.511 eV. So the difference in energy level is equals to E2 minus E3 modulus, which then you will get 1.889 EVs. And then in order to convert it into actual joules, you simply have to multiply by the elementary charge, which then gives us 3.022 times 10 to the power minus 19 joules. Alright, and as we know, E equals to HF, V equals to F lambda, lambda equals to V over F. Yeah. So E equals to H V over lambda, which is equal to Hc over lambda. The reason why we can change V to C is because we're talking about, electromagnetic waves, and electromagnetic waves all travel at the speed of light. So by rearranging the formula, we get lambda equals to Hc over E, where H is Planck's constant, C is the speed of light, divided by energy. Then you will arrive at the wavelength of 6.58 times 10 to the power of minus 7 meters to SF. Alright. Next question, explain why the energy of each energy level is negative. Simply put, it's a 1 mark question. I won't waste my time trying to fight for this 1 mark. So here's the answer. Nice. Alright, for the last question, please do read through the whole question. We'll go straight into answering. Alright. Calculate the maximum deceleration a Formula 1 driver experienced while braking to rest in a straight line. So it's mentioned over here. A Formula 1 car can stop in a straight line distance of 80 meters from a maximum speed of 185 kilometers per hour. So the first thing is we need to convert 185 kilometers per hour into meters per second. So 185 and 1 hour has 3,600 seconds. So if you do the math, you will arrive at 51.39 meters per second. Alright. And now this is kinematics. So there's 3 formulas we can use. V equals U plus AT. S equals to ut plus half at square, or v square equals to u square plus 2as. There's one obvious problem, there's no time involved, so these two are out, meaning we have to use this. So if we were to rearrange it, we're looking for A. So A is equals to V square minus U square all over 2S. The final velocity will definitely be 0, and the initial velocity is given by 51.39 meters per second squared, multiplied by 2 times the displacement, which is 80 meters. Yep, it's 80 meters. And you get an acceleration of negative 16.5 meters per second squared. And in the final answer, we do not include the negative sign, as they want to ask for deceleration, right? So acceleration being a negative value would imply that the car is decelerating. So yeah. Next, determine the maximum speed a Formula One car can travel around the tightest circular corner at the Singapore Street Circuit. Okay, so once again, so circular motion. You want to start off with the sentence of something providing for centripetal force. So in this case, when a car goes in a circle, in a tight circular corner, the frictional force provides for centripetal force. Okay, so the centripetal force experienced is mv squared over r. What about the frictional force? If you read this, the tires have to withstand lateral accelerations of up to 4g. 4g. So here you put 4 mg. Since the tires withstand an acceleration of 4g's, it means that the lateral weight, quote unquote lateral weight, that the car is experiencing will be 4 mg, right? Where the weight is the weight of the car, right? Now in this case, the masses will cancel out, and we simply have to solve for v. So v is just the square root of rg, where r is 30, and g is just 9.81. So if you work it out, oh, I forgot the 4. If you work it out, you get 34.3 meters per second. Nice. Alright. By reference to figure 8.1 and 8.2, it suggests explain why the tires are heated before use. 8.1 and 8.2. Okay. So if you start from the top, it says that before use in a race, tires are kept warm in special tire blankets. Kept warm. And if you look at the x-axis, as the temperature increases from 0 to 80, or rather from some value to 80, the coefficient of friction reaches a maximum. And given by this formula, as you can tell from this formula, if the coefficient of friction will give rise to the largest value for friction when it is at a maximum. So optimally, we want the tire temperature to be as close to 80 degrees as possible, because any temperature below or after that will cause the coefficient of friction to decrease, right? Now let's look at figure 8.2. As you can see, this is the tire at 20 degrees. The tire at 20 degrees. When the tire is heated with a tire blanket, the compound of the tire becomes softer, increasing the circular contact area. So when the tire is heated to a higher temperature, it will start to essentially sink into the gaps. Quote unquote, it will sink into the gaps, thereby increasing the surface area, thereby increasing the friction coefficient, thereby increasing the friction between the wheel and the ground. Right. So in order to answer the question, suggest and explain why the tires are heated before use. First point, when the tires are heated, they become softer, fill up the air gaps. When the tires are heated, they become softer and fill up the air gaps between the tire and the road. What does this do? This increases the amount of surface area of contact. This increases the surface area of contact, hence it increases the coefficient of friction. Alright. Now the next point. So that's using figure 8.2. Figure 8.2 tells us that when the tires become softer at higher temperatures, it will become softer and hence it will have greater surface area of contact between the wheel and the surface. Right. But what about figure 8.1? Figure 8.1 tells us that the optimal temperature to maximize the coefficient friction is 80 degrees by F equals to W. Right. So when the coefficient of friction is at a maximum, the force will also be at a maximum. So what does this allow? This allows for greater acceleration, deceleration, as well as higher lateral frictional force, allowing the car to navigate tight corners better. Right. Next, cross-section area of the rear wing on a Formula car is shown. Right. The wing deflects air when the car is moving, explained by reference to the change in momentum of the air, why this air flow appears to increase the weight of the car. Whenever you see change in momentum, you should think of Newton's second law, where force is directly proportional to the rate of change of momentum. Right? So, we start off by saying that as the air is deflected upwards by the wing, they experience a change in momentum. They experience a change in momentum upwards. Since there is by Newton's second law, since there is a change in momentum, the air has experienced a force, a resultant force. And now, since we know that there is a force acting on the air that's causing it to deflect upwards, it also tells us that there is an equal and opposite force that is acting downwards. So by Newton's third law, the air exerts an equal and opposite force on the wing. So this force adds to the weight of the car and there is a greater contact force between the tire and the ground. Hence, airflow increases the apparent weight of the car. Nice. Alright, part D. They want us to show that this formula is true. So by taking moments about the center of gravity, start off with saying that the sum of clockwise moment about the center of gravity is equals to sum of anti-clockwise moment about the center of gravity. So if you were to take the point of reference to be the center of gravity, which are the clockwise moments? Clockwise moments are going in this direction, right? So the first one that I can see would be this one here. Moments due to rear contact force NR. Here's the perpendicular distance, right, between the line of action of the force and the pivot. What about driving force? Well, if you were to extend the driving force line, here's the perpendicular distance. You can see that the driving force actually creates an anti-clockwise moment about the pivot. Same with the normal contact force. Same with the moments due to normal contact force NF. So clockwise is NR, and anti-clockwise is driving force D and NF. Alright. So the clockwise is NR, force times the distance, which is XR. And the anti-clockwise would be driving force D times H plus normal contact force NF times XF. Oh, it's getting complicated. Times XF. Alright, so basically need to solve for NR. NR would just be DH plus NFXF all over XR. Done. Or so we thought. There's a problem here. The problem is the final answer does not contain NF. That's my NF, right? So basically we need to get rid of the NF. So how can we do that? Let's look at the diagram. As we know, the downwards force due to the cast weight is W, which there's an equal and opposite force, which are the normal contact forces, NR and NF. Right. Since we're solving for NR and we need to get rid of NF, what we can do is you can rearrange to solve for NF. So W minus NR. NF is W minus NR. So we're going to sub that in, right? DH plus W minus NR multiplied by XF all over XR. So as you can see, we need to move the denominator back, then expand this. So it gets kind of messy. So we're going to restart. We're going to straight away substitute in our expression for NF. So NRXR equals to DH plus XF multiplied by W minus NR. NRXR equals to DH plus W. I just noticed they were using small x, but it's okay. WXF minus NRXF. So we will move the final term to the left hand side. We will factorize out what we are looking for, which is NR. And there you go. That's the derivation for the formula. Right, now for part 2, determine a similar expression to that in D part 1 for NF. As we know, NF has this formula. W minus NR. And why is NR? NR has been found in the previous part. So we just substitute everything in. XF plus DH. XF all over XR plus XF. Expand it. Simplify. And we're done. That's it. For the next part, use your expressions in D part 1 and D part 2 to show that there is a weight transfer between the front and rear wheels. So the weight transfer So from this part here, when a Formula One car accelerates, the weight distribution between the front and rear wheels changes. The cars are rear wheel drive, meaning the accelerating force is provided through the rear wheels. When accelerating, the contact force experienced by the rear wheels increases, and this is called a weight transfer. So, you have to show that when the car accelerates, there is a weight transfer, right? So before the car accelerates, there's actually no driving force. So when there's no driving force, the D here disappears. Same with this, the D here disappears. So for no driving force, the normal reaction force in the rear wheel is equal to WXF over XR plus XF. While the normal reaction force in the front wheel is WXR over XR plus XF. However, when there is a driving force, the normal reaction force experiences an increase and becomes WXF plus DH all over XR plus XF. Same, however, for the normal reaction force in the front tires, it will actually decrease. It decreases to WXR minus DH all over XR plus XF. Right. This tells us that when the car experiences a driving force, the weight is transferred from the front to the back. A driving force from the front to the rear. So this shows that there is a weight transfer. Right, next. Calculate the maximum temperature increase of the carbon fiber brakes when a Formula One car brakes to rest from the speed. So, if you were to assume that all of the kinetic energy that the car possesses directly converts into thermal energy, you can come up with this formula. So Ke equals to thermal energy half mv squared equals to mc delta theta. Do take note, there is a slight difference between the m's. This is m of the car, this is m of the brakes. Alright. So if you sub in the numbers, the mass of the car is 750 kilograms. The mass of the brakes is 1.2. However, take note that there's one set for each of the four wheels. So meaning for one wheel, the mass of the brakes used is 1.2 kilograms. Alright. So the total mass has to be multiplied by 4. 750 multiplied by the speed. And recall that we have actually converted the speed from 185 kilometers per hour into meters per second. 51.39. The mass of the brakes, where the mass of the brakes is 4 times of 1.2 kilograms multiplied by the specific heat capacity times delta theta. So, if you were to solve for delta theta, you will simply get 183 degrees Celsius. State an assumption that you have made in E part 1. You assume that all the kinetic energy of the car is converted into thermal energy onto the brake, and none is converted onto the tires. Alright. So, suggest 2 reasons why the discs have many small holes. Well, one reason is that these small holes facilitate the flow of air through the discs to increase the heat dissipation. Because over time, the discs experience a lot of wear and tear at high temperatures. So, in order to increase the lifespan, you have the holes in the disc to allow the air to be dispersed better. So, it facilitates air flow within the discs, increasing heat dissipation, increasing lifespan. Now, the next reason is that in the event of rain, what the rain does is it decreases the friction between the tires and the ground, or rather the tires and the brake pads. So the holes that are made in the brake pads are able to disperse the rainwater away, which thereby increases the friction between the tire and the brake pad, in the event that it actually rains. So disperses the rainwater through the holes, increasing the friction
tyre and brake pad.